Alright, so now that we know how rate of changes, which is like velocity, apply to derivatives, the rate of change and a slope are synonymous. Now that we know that you can use derivatives to find rate of change and all other things, we can do a lot of fun story problems with these. And I'm going to be talking about using differential equations. Differential equation is the same thing as a derivative, although there is a more specific differential unit later in the year, but we're just going to consider right now to be like a derivative. And I'm going to describe this video through a story problem. Basically, I'm going to be telling you about how, if you know the rate of change of one part of an object, how much it's increasing, then you can find how much another part of the object is increasing. For example, let's say you have a circle, and you know that the radius is increasing by, I'm not going to do these problems, let's just say 2 centimeters per second. You know that the area is not increasing at a constant rate. The area is actually increasing more and more every second because the radius is getting bigger, therefore the r squared is getting bigger, and as we know, r squared is exponential, it's not linear, therefore the area of the circle is actually not going to increase at a constant rate just because the radius is increasing at a constant rate. So there'll be problems where it'll say, what is the rate of change of the area of the circle if the radius of the circle is increasing by so much? So actually, let's do a problem like this. So let's say that the radius, which we're going to call r, let's say the radius is increasing 2 centimeters every second. So how we write our rate is dr, how much the radius is increasing per second, we're going to do dt. So dr dt equals 2, because it's increasing by 2 every second. The slope of the radius line, if you were to graph one, which would be kind of complicated, would be 2. It's increasing by 2 per time, so dr dt is 2. And the question is asking what is the rate that the area of the circle is increasing when the radius is 5. Because once again, the dv dt, or sorry, not dv, the dA dt, if A stands for area, I'll write that over here. If A stands for area, we're trying to find dA dt. However, dA dt is not going to go up constantly. It's going to change every second because the radius is getting bigger and bigger. And for that reason, you need to have a certain time that you're going to be finding the rate for. So let's say with this problem that we're looking for the rate of change in the area when the radius is 5, when r equals 5. We're going to start off by knowing an equation that relates the radius and area. Luckily, we know one. We know that area equals pi r squared. Now, we have some information here. We know what we're solving for. We're solving for this, and we know this. There's no t in here, though, and there's t's here. So we're going to have to actually take the derivative of this right here in respect to t, because we want to know what the rate is, and the rate is going to be in respect to time. So, d over dt. And this is where the chain rule is going to come in handy. You can't just take the derivative of a in respect to t and just say it's 1. It's 1 times dA dt because of the chain rule. Pull down the 2 using product rule, and you'll get 2 pi r times dr dt because of the chain rule. And I can get rid of this 1 times because it's obviously not going to affect anything. So this is the derivative equation, and we know some of these values that we can now plug in. So we're solving for the dA dt, so we'll just leave that on its own side. 2 pi times, we want the radius, which we know because we're solving for when the radius is 5, times dr dt, which is 2. So therefore, 10, 20, the rate of change in the area, if the radius increases by 2 centimeters per second, and when the rate of change in the area when r equals 5 is 20 pi centimeters squared per second. And that is how you can use derivatives to find the rate of change in different parts of an object.